Okay, welcome everyone. Thank you very much for coming. I'm Dani Servén Marín. I am a twin, and actually my twin brother is here along with his girlfriend. So these are two of my best friends in the world. So thank you very much for coming. But also, you are my friends as well. So thank you for coming to the talk. Yes, like he said, I'm a full-stack data scientist. I love researching machine learning problems, being creative with data, and deploying solutions to the cloud or whatever. I'm Spanish and American, and I love working on problems that impact and improve our society and our environment and our people. I also love the DIY ethic, so this is part of the reason I started making this package, and contributing and learning from the open source community. So pyGAM, like you said, is a new library for fitting generalized additive models in Python. I've tried to make it really modular. It's written in pure Python, which makes it easy to deploy and integrate into your work stream. And it plays nice with the rest of the PyData stack. So it's easy to, if you know scikit-learn, it should look familiar. The fit and predict methods are all similar. It integrates with grid search and the randomized search. And it's also very easy to extend the typical regression and logistic models with custom link functions and custom distributions. So this is part of the modularity that I've tried to start, and makes it easy to extend as well. So if you want to contribute, it's quite easy. So if you're familiar with R, you've probably heard of the MGCV package. The GAMs are actually quite popular in the R programming language, and there's some excellent packages out there. They're written by the people who developed the theory for generalized additive models. So the quality is amazing, and I encourage you to use it. And in fact, there's a talk later today about how to interface R and Python. So why would you even bother to come here? There's also a different package in Python called PyEarth that implements the Mars algorithm. But when it comes to fitting penalized regression splines in Python, there was no package. So I decided to step in and contribute back to the open source community. On top of giving, there's also a lot of receiving. So I get to learn a lot about statistical theory and improve my code quality, as well as learn about how it is to contribute to an open source project and what type of responsibility that brings with it. There's tons and tons of awesome parts of the Python pyGAM package that I would love to talk to you about, but we have so little time, so I can only talk about a handful of them. And really, we're going to focus on a regression task, and I think the easiest way to illustrate these properties is with an example. So suppose that we're here at PyData, and we have our own self-sufficient community. We're going to call it PyDatatopolis. And one of our tasks in our community is to generate our own electricity. So what we have to do is be aware and be prepared for the worst case scenario. So we should plan how much electricity we need to generate for tomorrow or for the days ahead. If we generate too little, we risk a blackout. And if we generate too much, then we're wasting our precious resources. So since we're at PyData, we decided the best way to do this is with machine learning, and we're going to be data-driven. So we collect a data set, a historical data set. And we can see we collect a data set that has kilowatts for the building, the outside air temperature, as well as the cloud coverage, because we believe that the environmental effects are going to have some influence on the power that our building requires. So we look at the power for the building, and we see a couple of things. There's this kind of repeating pattern, which is the weekly cycle, and then also this sort of trend that's going from high in the beginning to low at the end. So maybe in the beginning of the year, in 2010, for some reason, the building was less efficient and was using more electricity, and towards the end, the trend, the baseline of the building was using less. But then there's also this multiplicative effect where towards the middle half of the year, the amplitude increases. So there's all these interesting features in this data set. And zooming in, we see indeed this weekly cycle. So we have these 5 spikes and then a rest period of 2 days. So this corresponds to the weekdays and then the weekend. So we go to our super powerful machine learning toolbox, and we get our LSTMs, our our Remax, nearest neighbors, RBF, SVM, whatever. We make an awesome model. We get an amazing fit. So we're excited. So we go to the rest of the people at PyDatatopolis and we say, we got it. I got the prediction for tomorrow. Here you go. But our friends are skeptical, and they start asking a lot of questions. And they're like, okay, so how sure are you that this prediction is correct? It's quite a big deal. If you predict too low, the building will shut off. And if you predict too much, we're wasting our energy. You should really be giving me an interval. That way I can prepare against the worst case scenario. That's a good question. Someone else says, Did you even bother looking at the weather for the rest of the year? It's going to be a hot summer. How does weather influence the power that our building requires? How should we prepare for this hot summer weather? Okay, good question as well. Someone else says, what about the cloud coverage? I want to know about that. How does that influence? And someone else just literally asks, etc. So all these people are asking random questions. So you go back to your toolbox and you try to evaluate, all right, my linear models, well, that would be perfect. Just as interpretable as I need. I can just look at the coefficients and decide what influence it's going to have on output, but there's too much bias. They're not flexible enough to fit my data. And all of the powerful models I have cannot be decomposed. They're black boxes. The Remax, well, maybe that's an in-between, classical time series method. But at the end of the day, it just gives me a bunch of coefficients out, and I don't know what to do with those. So you just spend some time surfing the internet, and you read a blog post about GAMs. And it sounds interesting because it says that the prediction is based off a bunch of independent feature functions that are added together. So you can inspect the contribution from each feature. Sounds interesting? So you pip install pygam. Okay, cool. So now we take the data set, add a couple of dummy features, for example, the day of the week, because we thought that this was a pattern that we identified, and a time of the year, because we want to perhaps fit a trend. We instantiate it just like we would our scikit-learn thing, and we say gam.fit xy. Cool, looks pretty reasonable. This is our prediction. This is the target data. Looks pretty reasonable. I mean, there's a couple of differences, but the overall trend is there. All right, not too bad. So we look in the documentation and we say, I want to see what these feature functions are all about. How does my output depend on the inputs? So we check the documentation and we say, partial dependence functions. That's exactly what I want. Give me the dependence functions and a confidence interval around them. Cool. So already we see that day of the week feature that we identified is kind of there. These 5 lumps and a two-day rest, modulus whatever day of the week. We see that yearly trend, which started high and it ends low, kind of like we identified. And here we have the 2 weather variables that we saw. This kind of quadratic dependence on temperature, that's interesting. So we can already answer that one person's question. And then this other cloud cover, we have no idea what's going on there. What the hell is that? Okay, so this day of the week thing looks cool, but it might be too smooth, right? Let's try to change the default. Let's add 100 splines for that feature. Looks okay. I mean, looks fine. I don't know what to do about that. Looks cool. Great. Can we answer this first person's question about the uncertainty? It turns out that yes. We can just give them we can give them a prediction interval. So we plot that, our average prediction, as well as a prediction interval around it. And here's the target for the next couple of days. We got lucky. We always guessed an interval that contains the actual prediction, that contains the actual data. This doesn't always happen, but we got lucky. So great, we satisfied 2 of the questions, but we still have some open questions. Namely, how do we choose the correct amount of smoothness? We did this super arbitrarily, right? We said, give me 100 splines until it looks more or less right. How do you do this in a disciplined way? And what can we do about that cloud coverage feature? Can we do some sort of feature selection? Cool. So I guess let's take a moment and step aside. We'll answer those questions later. What are GAMs? Whoops. This is a trick question. Okay, so who here has ever fit a linear model? Awesome. Who here has ever fit a GAM? Dude, more than I expected. But it turns out that everyone that's fit a linear model before has also fit a generalized additive models because it's a specific case. For the sake of this talk, we're going to refer to generalized linear models as linear models, just for the sake of simplicity. So once again, who here has ever fit a generalized additive model? Nice. All right, cool. So let's recap. A linear model, as we know, it fits 1 coefficient per dimension of our feature vector. So at the end of the day, what we have is 1 line per feature, and we can sum them together and make a prediction. A generalized additive model is quite similar, but instead of a line, we fit a possibly nonlinear function on each feature. This is in the simplest regression case. In general, our feature functions can have interactions of features, which in practice is often important, right? Like, we need to know in one region of feature space the function should do something, in a different region of feature space it should do something different. But we're going to restrict ourselves to the simple case. and regression at that. Realistically, GAMs can also model any exponential family distribution on the error, and as well as link functions. But we're going to constrain ourselves to the regression case. If we take our whole machine learning toolbox and we organize them by predictive power and interpretability, we might get something like this. Modulus, the fact that I have a point to prove here. So we'll see our predictive and uninterpretable neural networks on one hand. Of course, if you have a multi-layer perceptron and you alter one feature of the input neurons, you have almost no idea what it's going to do to the output, especially when you move to a different region of feature space. Perhaps in one region it increases the output, and in a different region, changing your input decreases the output. It's quite a black box, right? Same thing goes for RBFs with SVMs and some of your other favorite powerful tools. Linear models, on the other hand, super interpretable, right? You just look at the coefficients, but they have quite high bias sometimes. It turns out that GAMs are just linear models. So they have just as the same interpretability as linear model and almost the same amount as predictive power. This slightly lower predictive power is actually a gift because it's what makes our model so interpretable. So what is a GAM? It's an extension of a GLM, and all it does is it adds splines and a smoothing penalty. We'll come to the smoothing penalty later. A spline is a function that is non-zero on a very small interval, and it's built out of low-degree polynomials. So the simplest spline is just this box function. And there's this really cool property, which is that if you convolve splines, you get a spline of 1 degree higher. So we convolve these two box functions, and we get a spline of degree 1. The cool thing is that this spline has a continuous zeroth derivative, right? It's a continuous function. So what we'll see in general is that a spline of degree n has continuous n minus 1 derivatives. And this, it also has n minus 1 segments, or n plus 1 segments. So we convolve the two linear splines, and we get a degree 2. We convolve those two, and we get a degree 3. Here we stop. It turns out, in practice, a third-degree spline is as smooth as we need to get for things to be visually appealing. There's a cool property as this one as well, which is that they have, like we said, continuous second derivative. So no matter how many of these degree 3 splines we add together, the overall function will have a continuous second derivative. In the limit, if we keep convolving splines like this, the limit is a Gaussian. And it kind of makes sense, right? A Gaussian has infinite derivatives, and we would expect that a function that has a spline of degree infinity would have infinity minus 1 derivatives, which is infinity, right? So intuitively, it seems satisfying. Cool, so now that we know how to build a spline, let's see how we actually build these nonlinear functions. We take our splines and we lay them out in a grid. And then we give them each their own coefficient, so a different weighting. And then we add them up, and that's our feature function. I'm going to try to convince you that this function, even though it looks nonlinear, we can estimate it and fit it using linear methods. So let's take a look at the most simple GAM, a function of just one feature with whatever normal error, So let's break this up. Like we said, we have that sum of spline functions, each weighted with their own coefficient. But it turns out that since we know those spline functions a priori, we can just evaluate each spline function at the x. Right? So now, that spline function evaluated at the x, we can just replace that with x hat. Just pre-compute them. This sum is just an inner product. So now, our function, our functional form is the same as a linear model. So a GAM is just a big GLM. This is a big deal because it means that we get a ton of statistical theory for free. We get to do model introspection. We get to learn about our model variance, the uncertainty we have in our predictions. We can extend it to a bunch of stuff, blah, blah, blah. We get a lot of statistical theory for free. This is a big deal. Everyone gets machine learning. And then we get a lot of specific GAM things for free as well. We get an intuitive regularization parameter, which is called smoothing, and we get the ability to model nonlinearities automatically. Cool. So GAMs are great, right? They have all these great properties. So coming back to smoothing, how do we do that? Let's go back to this, this example. So we chose the number of splines and that smoothing stuff totally arbitrarily till it looked nice, huh? What we were trying to do really in that example, well, let's go back to that. So look at the outside air temperature, this one in the bottom left corner. it has, it's quite wiggly, right? Like, it's got an overall quadratic kind of looking shape, but why is it so wiggly? Like, is that wiggliness, significant? Is it really important for our predictions? Same thing with like the yearly trend, right? Like, what's up with all that? Can we smooth that out more? Should it be less smooth? And the cloud coverage, the confidence interval around that is quite wide, so why is all this wiggliness in there? Can we just eliminate that stuff? It turns out that we can be a little bit more disciplined about the definition of wiggliness, and we can quantify it like this by taking the integral of the square of the second derivative. It kind of makes sense, right? Because the second derivative measures curvature. So if we square that, we always get a positive number. This way, negative curvature and positive curvature have the same effect, and then we integrate that. So now our objective is that linear objective that we saw earlier from the linear model, as well as this wiggliness objective. And we can tune how much we care about wiggliness with this lambda parameter. So a high lambda means that we penalize wiggliness really heavily, and a low lambda, if it's 0, we don't even care about it. It turns out that we can approximate the numerical derivatives. We can approximate that second derivative using numerical methods. This matrix S takes the numerical derivatives, and then we can do the integration using this quadratic inner product with the betas. So this is our functional form. If we look for the closed form solution of this, it's as follows. And this is kind of nice because it looks familiar to the solution to ridge regression, which is intuitively, satisfying. We're not getting something totally crazy with generalized additive models. All right, so how do you do this in practice? Let's make some random data, blah. Kind of cool. You can kind of see like a signal, right? This expanding sinusoidal curve. So let's try it out. We take a GAM and we make it extra flexible. We put 50 splines in it. So we have, the potential for a ton of wiggliness, tons of degrees of freedom in here. And we make a super high smoothing penalty, 1 million. So we'd expect a very high penalty on wiggliness. And we fit it, and we get almost a straight line. That makes sense, right? There's a cool feature in pyGAM, which is the model summary, and it gives you a bunch of information. One of the things I've highlighted is this effective degrees of freedom. So out of those 50 spline functions, this supermassive smoothing parameter of 1 million has crushed the flexibility of the model to just a straight line. So that's nice. Let's go the opposite way, right? Let's make the lambda 1 over 1 million. So we have almost a 0 smoothing parameter. And now we get something that's the opposite end of the spectrum. The left side is like clearly just fitting noise and just the variance in the noise. We would not want our fit to be like that. And if we look at the model summary, we get a model that's indeed almost as flexible as the potential, as the number of lines we had. Okay, so the smoothing penalty is kind of doing its job. So how do we do the right amount of smoothing? Let me take a drink of water. Well, the obvious choice is cross-validation, right? It's been up there for a few seconds, so. Right. Since our generalized additive models are an extension of linear models, we get to do generalized cross-validation, which is a super fast linear algebra approximation to leave one out cross-validation. This is great. It means that we don't have to do this tedious, split everything into folds, take the average of the loss across the folds, find the parameter setting with the lowest loss. Take that for granted. We can just evaluate each model one time and get this GCV score. Hyperparameter optimization, this smoothing parameter selection, is not an afterthought in pyGAM. All you have to do is replace the fit function with this grid search. And if you want to be even more specific, you can specify the grid at which you're looking. So here we specify 100 different functions, 100 different parameter settings. And we get that the model decides that 25 degrees of freedom is the best choice. And it looks quite nice, too. Not too straight, not too wiggly. Cool. So we kind of know how to do this. Let's go back to our PyDatatopolis, our city, our self-sufficient city, and let's choose the best model. Since we have 4 features, that we have 1 lambda parameter per feature. In theory, we can smooth the yearly trend very heavily while keeping the weekly trend very flexible, right? So we have 4 lambda parameters. This is a 4-dimensional search space. It would make our grid search really infeasible. So instead, we get a little lazy and we just choose a random search. So I randomly generate points in a 4D grid and grid search across them. And we get something like this, which kind of is a lot nicer, right? All the wiggliness of this temperature and of the yearly trend are eliminated. It turns out that the model decides that a more smooth day of week predictor is better. Okay, whatever. And all the wiggliness of the cloud coverage is out of there. That's great, because it means, yeah, it didn't look like it mattered, right? But the confidence interval around the cloud coverage is still really wide. What's going on with that? So again, we turn back to the model summary. And we look at the p-values and the significances for each feature. Indeed, the significance for that feature is super tiny. It shouldn't matter at all, right? So we can, I guess the best thing to do is we just eliminate that feature going forward. But I've kind of lied to you guys this whole time. I made that feature using random data, so of course the model should choose that it's insignificant. And in fact, if you look closely at the other p-values, you'll see that they're all identical, right? They all have this 1.11 e to minus 16. This is actually something that we have to change. That's a bug in pyGAM. So that's an issue that you can check out on the GitHub and, help out with. But there's also a lot of really cool stuff, right? Like there's all these cool features I didn't get to, but there's a lot of awesome features that we still have to add to make this library even more powerful. Feature interactions. The reason we're focusing on functions of just one feature at a time is because so far I don't have that syntax. I don't have the semantics in there for the library. And a bunch of other really cool stuff that are just going to make it much better. And so I definitely encourage you, if you've been inspired by this talk, check out the GitHub, check out the issues. There's a bunch of good first-time contribution things, whatever. Help out. So thank you very much.
Thank you very much, Dani. I would have a ton of questions to you, but probably offline. Let's give the audience the chance.
Okay.
Hi, Dani. Thanks a lot. Great presentation, great program. How does it compare with Profit, which I'm pretty sure you're also familiar with, because they are both GAMs?
Yes.
What's your view on that?
Yeah.
And the second question, more content-driven, is for your city, how good is the weather forecast, and is weather really usable? Because my experience is beyond, let's say, the next 4 hours, it's not so easy, and beyond the week, beyond 2 days, it's really random.
Yeah. All right, great. I've used Profit only a little bit. The Profit is this generalized additive model software for building time series GAMs, and it's made by the Facebook team. I've only used it a little bit. It was kind of cool. It has a bunch of cool features for automatically detecting change points in your time series. So it's got all those great features, and it's built for time series. So I guess this is both a feature and a limitation of the software, right? Like, as far as I can tell, it's not easy to adapt it to non-time series problems. One of the other things that, it's going to have very few bugs. It's going to be very well maintained. That's an awesome plus. One of the things I don't like about it is the API. I think it's kind of clunky, and especially coming from this PyData scikit-learn API stuff, I find that way more intuitive. And but honestly, it compares quite favorably. I was implementing these time series models that I was showing you guys. I was actually implementing them at my previous company, and I was comparing both Profit and pyGAM. And I had a stake in pyGAM, of course, but I was comparing both of them. And the prediction intervals were super consistent between both of them. So it was a coin toss to me at the end of the day. And for your second question,
go ahead.
Which was about the city, the prediction, the temperature of the city. Right. Correct.
Beyond, let's say, a couple of days, weather forecasts are not very usable.
Yeah, for sure. The way that I dealt with this, I think I'm practiced. Yeah. Well, yeah. I don't have a good answer for you. I'm sorry. Besides the fact of saying that this is a toy answer. In fact, there's actually a lot of problems with the example I gave you, which is that, of course, we did the grid search for the best model using this generalized cross-validation score, but in fact, that assumes that each sample is IID, identically distributed, whatever, independent. But in time series, they're not. So already we have this. That would actually not be the right cross-validation criteria for this specific problem. In theory, we would really want to use this kind of nested time series type of cross-validation.
Yeah. If I can add to that very quickly, answering your question, I actually did compare Prophet and GAMS, and I can tell you that the GAMS combined with in an ensemble with another method beat Prophet. Depending on the application, it was either support vector regressions or random forests. And it was actually an ensemble. Okay. Any other questions?
Thank you for this great talk. I want to ask if generalized additive models also suffer from the multicollinearity or like other linear models.
Yes, that's a great question. So do these suffer from collinearity in the features? Yes, they do. In fact, there's a specific measure for these types of models called concurvity. That's another thing that we have to add to the package as well, and we could add into the diagnostics of the summary. But yes, they do suffer from this problem, and we have to. You can estimate the amount of collinearity, and then try to address your feature selection based on that as well. But that is a really good statistic that should get integrated to the package as well.
Hi, great talk and great package you have there.
Thank you.
Maybe this is a dumb question, but how can GAM be so interpretable as a linear model if your function, if each feature has an arbitrary function, a potential arbitrary function?
Right. The reason it's so interpretable is because we are, at the end of the day, only adding these nonlinear functions together. So if we were doing something more complex, like multiplying them, and then in a second layer doing a different transformation on them, like a neural network would do, then yes, of course, it would be very difficult to interpret. But since we're only doing a very simple operation to combine these nonlinear functions together, which is just the summing operation, that's what keeps them so interpretable.
Sorry, but do those functions in this adding operation have their own coefficients?
Right, so...
Because I don't remember the formula.
Right, the formula is that for every feature, we allow several splines, and each spline gets its own coefficient, and then we add those splines together. So, but the thing is that at any given point, our prediction only depends on the sum of several different feature functions. So I want to say, how does my output depend on feature 1? I would just look at the only feature function that depends on feature 1, which would be this set of splines, one nonlinear function. If I want to see how my output depends on feature 2, I would look at the only nonlinear function that has feature 2 in it. So I would look at that spline function.
Got it.
I hope I...
Thank you for your talk. Check out your package. So I have two quick questions.
Yes.
The first one is I wonder if you have ever benchmarked against like Gaussian process libraries, since GAM and Gaussian process mathematically they are quite similar.
Yes.
And the second question is that in terms of like non-Gaussian noise, is pyGAM also built in to kind of handle these situations?
Yeah. Cool. So I have not benchmarked against Gaussian process, and like you said, it's a very beautiful relationship that they share together. What I know for sure is that the estimation is much faster for pyGAM because you can just use it. You estimate it using least squares, whereas for Gaussian process it's much more complex. But I guess, of course, yeah. Anyways, the long story short, I have not benchmarked them, but it's a super good question. In fact, I have hardly benchmarked against. Officially, I don't have any benchmarks on the documentation, which is missing as well. But yeah, it's a really good point. And I forget what the second question was.
It's about non-Gaussian noise.
Oh, yes. Oh, yeah, I would like to show you, actually. I didn't have enough time. This is one of the things I really wanted to show you guys today. But you can easily fit functions with non-Gaussian noise. So if you have, whatever, regression problem is Gaussian noise. If you have a classification problem, this is binomial noise. You can easily fit pyGAM using this. We also have the potential to fit Poisson models using Poisson distribution. So you can do histogram smoothing or model count data like this. And in general, any exponential family distribution, you can model it in this software very easily and very modularly. Thank you. Good opportunity. Okay.
One more question over
Thank you for the talk. I personally use GAMs now, and I started to use them with this package actually. But I wanted to ask if you compared pyGAM with MGCV package in terms of performance.
Yeah. So he's asking if I've compared pyGAM with MGCV. MGCV, I think, in my opinion, is like the gold standard GAM package because it's written by one of the top researchers in the world that studies GAMs, Simon Wood. And in fact, the whole package that I wrote for pyGAM is based on the textbook that he wrote about GAMs. So in a sense, yeah, it's heavily inspired by the MGCV package, and in fact, it's trying to be a clone in many ways. And a lot of the tests I run are comparing, well, how does the model summary perform against the model summary, the equivalent model summary of the R package? So I've only compared it in that respect. But yes, it's super inspired by the MGCV package and can only hope to be as good as it at some point. But also modular in its own way and more intuitive to Python stack users in its own way as well. Yeah.
Any further questions from the audience? If not, thank you very much. This was a session on explainability and privacy. Thank you to Dani once again. And I think we have a break now, don't we? Yes. See you there.